Carly McAvoy doing homework 7A, and let's take a look at the assignment on paper. 7A, we start to move into some things that are a little different than what you've been doing. I think it's kind of fun, but chapter 7 and 8 typically people think are the harder chapters, so just don't ease up now. A newspaper provided a snapshot illustrating poll results from 1910 professionals who interviewed job applicants. The illustration showed that 26% of them said the biggest interview turnoff is that the applicant did not make an effort to learn about the job or the company. The margin of error was given as plus or minus 3 percentage points. What important feature of the poll was omitted? Well, they talked about who the population was at the sample, and they talked about the results, 26%, and then they also said the margin of error was plus or minus 3 percentage points. But what they didn't talk about, which is always important when you talk about a survey like this, is the confidence level, or the confidence level. Because every time you say that, you say I'm 95% certain, or I'm 98% certain, or 95, 99, whatever it is. That's something that you have to give. So they didn't talk about what percentage, how confident they were with their results. So the confidence level was the answer for that one. Okay, find the critical value, Z alpha over 2, that corresponds to the given confidence level. And they're talking about 81%. So let me draw you a picture of what we're talking about here. When we talk about 81%, remember that the entire area under the curve, which we can talk about as being 1, or we can talk about it as being 100%, that's the whole area under there. These lines never actually touch. They get closer and closer as they go out. They don't actually touch, so it always kind of hovers. And we know that if we go right down the center here, to the left of that is 50%, and to the right of that is 50%. And that line down the middle is the mean, and then it's 50% on either side of that, 100% total. So what they're talking about here is 81%. So we were talking about, let's say this area is 81%, which we can think of as 0.81, right? And so what there is there's two tails, one on either side that has some area. That's where we get this divided by 2 thing, because we have basically one whole, and we're subtracting off the 81% in the middle, which is 19%. But there's 19%, it's alpha, it's 19%, but it's divided up into 2 equal parts. So we divide by 2, and then we can say what is actually on either side of the tail, right? So half of 19 is 9.5. And so the Z alpha over 2 is actually 0.095 in this case. So this is 0.095, and this is 0.095 over there. Now, you can use a table to do this. So we're going to use our calculator. What they're asking for, if we go back, is to find the critical value, and that is the Z value right here. We just give it a positive one. We don't have to give both of them, but there's 2 different ones that corresponds to that confidence level. So we're going to put it into our calculator. We have the area, and we want to find the Z, so we're going to use inverse normal distribution and down to inverse normal. We know the area of our little chunk is 0.095. Now when I put that in, 0.095, this is for 0 and 1, a mean of 0, a sigma of 1, or a standard deviation of 1. When I put that in, what it's going to assume that I'm looking at this part over here. It's not going to think that you're jumping over here, because they always are thinking about what's to the left of the number that you give. So we're looking at this point and to the left. So it's going to give us a negative value. How do I know? Because I know that the Z-score that's to the left of 0 is going to be negative, and I want the positive one of those, because I always just give the positive, but there's actually a positive and a negative. There's 2 different sides there. So I know ahead of time I'm going to get the negative, but I don't give that as my critical value. So this says to 2 decimal places, so it's going to be 1.31. All right, it's actually negative 1.31 and positive 1.31. That's what we call a critical value for 81%. All right, so that's where they get the answer 1.31. All right. Number 3, find the critical value that corresponds to alpha being 0.10. Notice that we want the one that's alpha over 2, so we're going to start off by, we're going to start off by dividing that by 2. So we're going to take 0.10 and divide by 2, because this z value they're asking is the half, just the half on that one side. In other words, we're going to get 0.05, right? And so if I look at it here, what that tells me is that I've got 0.05 over here, I've got 0.05 over here, so how much did I have in the middle? Well, what I had in the middle was 90%. 10% on either, that adds up on either side, and 90% in the middle. And so I'm looking for the critical values there, and again, I'm only going to give the positive one. But I'm going to do the same thing again, putting in 0.05 and 0 and 1, and then hit that, and I get negative 1.64. And this is a thing about that, is that my calculator rounded it a little differently than theirs. That's fine, don't worry about it. If on the test, when you do something in the test and it's off by a decimal point like that, I would go back through and give you credit. And the program itself is made up to be a little lenient in that way, so I think they would take 1.64. But 2 decimal places takes you to that. So this is actually 1.65 negative, and this is 1.65 positive, and that's our critical values there for that. Okay. Express the confidence interval that goes from 0.333 up to 0.777 in the form of p hat plus e. So e is our margin of error, and what I know is that I have some p hat, and I add the margin of error to get the higher bound, and I subtract the margin of error to get the lower bound. And so one of the things I can do to figure out what my actual middle point was is take the average of these two numbers. So to find p hat, I'm going to take 0.333 plus 0.777, and I'm going to divide by 2. And that's going to give me, you can do it yourself, but I'll do it. 0.333 plus 0.777 is 1 whole, right? Nope, it's 1.11. Yeah, good thing I didn't do that. Divided by 2 is 0.555. So that's my p hat. And so what did I subtract or add to get that? So then I just go back and say, take the higher one, let's say 0.777 minus 0.555. That means I must have been adding on 0.222 for this middle thing. So in other words, I took 0.555 plus 0.222, and I got the higher number, 0.777. And over here, I took 0.555 and I subtracted 0.222 to get the lower number, 0.333. And so my p hat was in between those two values. So I found that by finding the average, and then I just subtracted it to find the rest of it. And that's how I get those two answers. The other thing you can do to get those two answers is to subtract. I'll do the p hat the way we just said, but to find the e, you could subtract 0.777 minus 0.333. Instead of adding them, subtract them, and then divide by 2, and you'd get 0.222 that way. There's whichever way makes sense to you, but that's probably how I would do it. All right, number 5, they're asking you to write this interval. Now they've given you the interval, and they want you to write it in this format. In other words, they want you to write the subtraction of that and the addition of that. When they write it this way, 0.019 up to 0.111, that really shows you 0.019 is less than p is less than 0.111. It's the same thing. This is an interval notation. This is an what do they call that notation? Inequality notation. So here they just want you to type those two numbers in. They want you to recognize that in the first box would go the 0.019 and in the other box would go the 0.111. So they just wanted you to write, here's your answers here. It's just all I'm trying, the reason I put that one in there is just want you to recognize different ways that you can write the interval notation. The other way you could write this problem, well, I don't know what I don't want to go through. Well, let's go through it. If I wanted to find out what the P was in here, sorry, P hat was. Oh, P's in the middle. Yeah, P hat is what you add to, sorry. Yeah. If I wanted to find that, I would take 0.019 plus 0.111 and then divide by 2, and that would give me the 0.065. Sometimes you'll see this, 0.065 plus or minus, and then to find the other part, I would take, remember that 0.111 and subtract the P hat, and that would give me what I'm adding or subtracting on both ends. So this is the interval notation. This is the inequality notation, and this is the same confidence interval stated in the plus minus format. And what that's telling you is that you would subtract this number to get the lower half, and you would add that number to get the upper half. So those are three different ways to say pretty much the same thing. So you'll see all three of those as you go through. Okay, so use the sample data and confidence level given below to complete parts A through D. In a Research Institute poll asked respondents if they felt vulnerable to identity theft. In the poll, N equals 1083, X equals 582, and who said yes, and use a 99% confidence level. Well, what's the best point estimate of the population portion P? When you're doing the population portion P, the best point estimate, what do I have all here? If they want the number, I was asking if they want, yeah, it's going to be P hat. So what you're going to do to find P hat, remember, is to take your X, say this many people said yes out of this many people who were asked, and that's going to give you your P hat 582 divided by 1083.537 to 3 decimal places. So 0.537 is going to be your best point estimate. Your estimate that you have, the best estimate you have, is your P hat for your P. P is the population proportion, P hat is your sample proportion. Identify the value of the margin of error. So we need the little formula for margin of error, and I think it's P hat plus or minus standard. Oh, we need the confidence level number. So what's 99? Well, if you think about this, we have 99% here. So we want to know what are those z-scores here, and we really only care about the positive one, but just remember they're both there. So what's left over after we do this? So we would take 1 minus 0.99, and that leaves 0.01 left. But we always want that divided by 2, right, for our z-score. So we're going to take 0.01 and divide by 2, and that's going to give us 0.005. So we have 0.005 on either end, and that's going to help us to find the margin of error, which we need to have that critical z-score. Okay, so I'm going to do inverse normal by doing second function data, distribution, inverse normal. I have 0.005, 0 and 1, and then I get the negative 2.5, how many places? 4 levels. 2.576 on either end there. Okay, so the value of the margin of error is our z-score divided by the square root of, formula is escaping me. I think it's the square root of n, but what number is this? 6. Here's what I would do. Jump up to number 6 and get that formula. That's what we did. Oh, yeah. P hat. Oh, yeah. Okay, I did not have it right. Z pi over of that times the square root of P hat Q hat over N. Glad I checked. Okay, so that's what I needed. Let's go back and do the work. So we just found out what this was, which is 2.576. So I have 2.576. It's going to change things how you round that. If you round that to 2.58, it's going to be a little different. Usually there's a tolerance built in, as I've said before. I know that the P hat was 0.537. How do I find Q hat? Well, Q hat is just 1 minus that, right? And the N here was 1083. So all I have to do is say 1 minus 0.537. Well, I didn't do that right. 1 minus 0.537. And that gives me 0.463. And then I have to do that problem. And so the way I'm going to do it is just to put it in as I see it, 2.576 times second function square root. And inside there I have a fraction, so I'm going to do that. 0.537 times 0.463 over 1083. Now I've just entered it. I haven't done a piece and rounded it, done another piece and rounded it. That's when you start running into trouble when you do that. So try not to. Just put it in. If you have this calculator, or if you have a different calculator, put it in as you see it, and then it won't have all the rounding errors. So I get 0.0390. I'm just rounding up. That's my margin of error. To find my confidence interval, identify them. I have 0.0390. Yep, that's what they have. 0.0390. That was the margin of error. Their box is too small for me. All right, the confidence level, P, is less than or greater than. I have to take my P hat, which is 0.537, and I subtract my margin of error on one side, and I add it on the other side. And that gives me my range of values. So 0.537 minus 0.039. The O and the N doesn't really change anything, but that's 0.498. And 0.537 plus 0.039 is 0.576. So that's this little part. These two parts right there are right here. Here's the first half and here's the second half. And I got that by subtracting the margin of error and adding the margin of error to my P hat. All right. Write a statement that correctly interprets the confidence interval. Choose the correct answer below. All right, so we have a 99% confidence. So we have, that's our confidence. That doesn't say that 99% of the sample proportions fall between those. We're not saying 99% of our values fall in here. What we're saying is we're 99% sure that the value that we have for the mean falls within here. Okay, so we're just saying the mean that we found, we're 99% confident that that's where it is. Plus or minus, that. We have the plus or minus thing. One has 99% confidence that the interval from the lower bound to the upper bound actually does contain the true value of the population proportion. That's what I think. We're 99% confident that it actually contains it. There is a 99% chance. No, it's not a 99% chance. It's not 99% of the sample. So those definitely no. I haven't read the other one. One has no. We're not saying 99% chance that ours actually equals. We're saying that here's a range and we're 99% confidence that our value for the mean would fall in here. That's what we're saying. I read that somewhere, so I think it was C. All right. So let's see if our values all came out. There's C, 0.576, 0.498. Those are all what I got, so we're good. All right. And then, of course, if you print out your stuff, they keep printing out these Z tables. We're using a calculator. Please do. Just get to use it. Get to know it. It saves you time and effort. So you'll see in number 7, they have printed them out again. It's quite inefficient, but that's what they do. So anyways. All right. Use the sample data and confidence level below to complete parts A through D. This is exactly the same as we just did. So you're going to go through the same exact steps, and when you do that, you'll have it completed. I will let you read this if you'd like to try it on your own to see how you do with it. N is 2502 here. Remember, for the margin of error, we just looked that up. It's going to be your Z alpha over 2 score, and that's going to be P hat Q hat over N. We know what P hat is by finding the 1161 and dividing by 2502, and we know what Q hat is because Q hat is 1 minus P hat, and then we know what N is. We know what Z is, 95% confidence. Just be careful with that piece. When you have 95% of your scores, that means you have 0.05 in these two areas. And so since we want to know what just one of those is, we divide by 2, right? And that gives us 0.025 in each area, and that's what we're going to enter into inverse normal. And we're going to put 0.025. The mu is 1, and the sigma is, mu is 0, sigma is 1, and this is our area under the curve over 2. So that's what you would enter, and then that's going to be what your Z-score is. That's how you find that, and that's what goes into the margin of error. The same thing we did before, but just different numbers. So I'm not going to work through it an identical problem. Okay. Number 8, a clinical trial tests a method designed to increase the probability of conceiving a girl. In the study, 560 babies were born, and 308 of them were girls. So when I'm talking about a probability like this, I'm going to say, well, I know that 308 divided by 560 is going to be my P hat. That's pretty standard, and hopefully by now you're getting that. That's just finding the probability, the proportion for our sample. Use the sample data to construct a 99% confidence interval estimate of the percentage of girls born. Based on the result, does the method appear to be effective? If you make a confidence interval and 0.5 falls within your confidence interval, then it's very likely that 0.5 would happen, which is what we would expect, and so the method's not effective. If you make a confidence interval and 0.5 is outside of that confidence interval, let's say your confidence interval goes from 0.51 to 0.57 or something, then you would say, whoa, wait a second. This doesn't make sense because our confidence interval doesn't include that known fact that it should be 50%. And then you would say, whoa, the method must be working. Does that make sense? So in the end, we want to look at our confidence interval and say, like, are we getting results that are outside what we expect? So to find this, you need two things. You need P hat so that you can add and subtract the margin of error. So you need the margin of error. The 99% I just worked out a few minutes ago, and I'm going to show you that again because I don't want to have to work it out every time. When it's 0.99, it's 0.01 left over divided by 2 is 0.005. And so this number, 2.576, is going to be the number that I use every time I'm given the 99% confidence. If you start to memorize those numbers that you see over and over, then you save yourself trouble of having to calculate it. So I'm going to take 0.55 minus, let's say minus first, 2.576 times the 0.55, which is P hat, 1 minus 0.55, which is Q hat, which would be 0.45, and divide by the entire sample, which was 560, or N, and that's going to give me the lower bound. Then I'm going to do that same thing with plus and get the upper bound. I might just find this E first. So let's do that. 2.576. And I don't even need to do the times here, but I have been doing it, so I'm going to stick with it. I could just do square root next to it. It's going to assume multiplication if you don't put a symbol in there. And then I did the fraction, 0.55 times 0.45, and then flip it down to 560 and hit enter. And what that gives me, 0.55 minus how many far are we supposed to go? 3 decimal places, so 0.054. And I'm going to do 0.55 plus 0.054 to get the upper bound. 0.55 minus 0.054 is 0.496. And the upper bound, this is nothing here. The upper bound is 0.55 plus 0.054. It's not that visible, sorry. Anyway, I want more light, but I don't want it in the picture. All right, there we go. Oh, that's not good. Anyways, I don't think you need to see me do those simple calculations anyway. So that gives you 0.604. So those are our two numbers, our two answers, 0.496, I can't say that for some reason, 0.496 and 0.604 go here into those two boxes. So those are the range. And so does the method appear to be effective? Well, no, the proportion of girls is not significantly different than 0.5. 0.5 is included in our interval. It's really close to the end, but it's still part of our interval. So it doesn't appear to be that different from 0.5, which is what we would expect. It's pretty close. If this was more like 58%, we'd probably get an interval that didn't include it. So in this case, no, because 0.5 is in there. But if I had something, like I was saying before, if I had something like 0.52 up to 0.57, we'd say, whoa, that is a little different, right? Because 0.5 isn't included. But here they didn't earn my respect on that one. Okay, page 8, page 9. Okay. I think this is the same type of problem, and I'm not going to work all these out. I want you to have an example of each type, but I also want you to do a little bit of exploring on your own. Let me just make sure. A genetic experiment with peas results in one sample of offspring that consisted of 415 green peas and 151 yellow peas. Construct a 95% confidence interval to estimate the percentage of yellow peas. So 95% is another one that I drew earlier. I don't think I worked it out. I think it's pretty easy though to go back and do that. We can do it if you'd like. Distribution inverse normal. We have 0.025, 0 and 1, and it's 1.960 if I round it to 3 places. So I'll give you that one. 95% leads to a Z over 2 score of 1.960. All right, so that's going to be the Z that you use. Same process as the last problem. The only thing different is that they told us green and yellow. So in order to get our N, our sample space, you need to add those two together. They didn't give you total. So N is 566. That's what you would divide by to find P hat, given, let's see, constructed the percentage of yellow peas. So our P hat would be the yellow, which is 151, divided by the total, which is 566. That's the only thing different in that problem. And then is it expected, what you're going to do is see, did the 25% fall within my range or was it not? If it's in my range, our confidence interval, then it's an expected result, just like normal. If it's outside of that, then you say, wait a second, I was supposed to get this many. So the confidence interval ranges from 0.23, just looking at their work, to 0.303. And so that was supposed to be 0.25, which is in there. So the confidence interval includes that. So the true percentage could easily be equal to 2 point. I think it got cut off there. I don't know, equal to, I don't know, whatever. just forget that. It could be equal to that 0.25 because it's in our range. So you can do that one. During a period of 11 years, this many people, there's our N, 42% were immigrants. 42% is our P hat, right? This is our N, but this is our P hat. They already did that for us, 42%. Use the sample data to construct a 99% confidence interval estimate of the proportion of grand jury members who were immigrants. Given that among the people eligible for jury duty, 59.6 of them were immigrants, does it appear that the jury selection process was somehow biased against immigrants? Already, it looks to me like, yeah, this is weird. Only 42% of them came in. There's a much higher pool of them to choose from. But we don't know until we do our confidence interval. And then when we do our confidence interval, we say, did this fall within our range? If it did, that's fine. If it's way outside of our range, we go, wait a minute, something's happening here, right? So the process for finding that's going to be the same. You're going to use your P hat, which was given, and then plus or minus your E. Your 99% confidence, again, we've been talking about 99% being 2.57. I have such a hard time remembering those numbers. 2.576, right? 2.576. Because we had 99%. If you can remember them, you don't have to go through the process of figuring out. I have to do them over and over. It's not, doesn't take long, but it's like, where is that? My brain does not hold on to those numbers. P hat plus or minus the E is going to give you your two numbers, and then you look to see what's in there. Let's see what the answers are. Their answers go 0.384. Great exercise is to try it while you're watching the video. Pause it and try it. See if you can get that. Now this is the range. We're saying the mean of the people that are being chosen ranges from 38% to 46% approximately. And I'm saying then, does that mean that there's somehow biased against immigrants? Well, we should be seeing, if they're being called the rate they're in the population, at about 60%. That is nowhere near what we have here. So yeah, something's up. Our confidence level's telling us that we would not get that many in us. If the selection process is going as planned, it's not going to hit that percentage. So yes, it does not include the true percentage of immigrants, so there seems to be an issue. Right? So that's that. All right, let's see if this one's the same. The brand manager for a brand of toothpaste must plan a campaign designed to increase brand recognition. He wants to first determine the percentage of adults who have heard of the brand. How many adults must he survey in order to be 95% confident that his estimate is within 6 percentage points of the true percentage population? Assume that nothing is known about the percentage of adults who have heard of the brand. Okay. We want to find out what that is. 95% confidence. We just calculated that again a couple of minutes ago. When it's 99%, it's 1.960. 1.960. We did that. I'm not going to go back, but you can go back in the video to see how we did it. We want to find N. I could go look that up, but you know, what's really nice is to have some algebra skills. Sometimes I just like to use my algebra skills, but here's what I know. E equals Z, I'm not going to write the little alpha over 2, but that's what we're talking about, times the square root of P hat Q hat over N. I want to know, I want N to be isolated, because that's what I want. I'm going to solve this for N. So let's do that. Let's first start by getting rid of that Z on the outside. Divide both sides by Z. And we have the square root of P hat Q hat over N. Then I'm going to square both sides. Square both sides. And when I square that, I get E squared over my Z squared. But when I square a square root, that just makes that go away. So I have P hat Q hat over N. I want the N on the top, so I'm going to multiply both sides by N. And that's going to cancel over here. I have P hat, Q hat. And then I'm going to get rid of this by multiplying by Z squared over E squared. all you need to know is what the formula is. I'm just kind of having fun with my algebra skills. All right, so we have z squared p hat q hat over e squared. All right, that's how we're going to figure out what the n is that we need for that. Cool. So I know what z is. It's 1.960. I'm going to square that. P hat. They didn't give me p hat. They didn't even tell me exactly how many people. So if you're not giving that, if nothing is known about the percentage, then we always assume it's 0.5. And that means that q hat would be 0.5. If they don't tell you, you assume. If they give you it, fine. If they don't, you assume it's 50%. And then we have the e squared. And the e squared we have to go out and find, huh? So e... What's this? How many adults must he survey in order to be 95%? Oh, here it is. 6 percentage points. That's my margin of error. I know it had to be given in there somewhere. 6 percentage points. So 0.06 or 6% is my margin of error. Okay. I couldn't find it without the n, and so I knew it had to be in there. Sorry, I didn't read through it thoroughly. So I have all the information I need. I'm going to go ahead and put this into a fraction. 1.96, I'm not going to bother with that 0 because it's not necessary, squared, times 0.5 times 0.5, which is 0.25, but I'm just entering it separate, but you could multiply those in your head if you want. And then down below, I have, I don't think I need parentheses, but I'm going to do it anyway, 0.06 squared. So that's my formula exactly as I see it. And I can hit that and I get 266.7, let's round it to 8. Okay, I need 266.78 people. Well, I can't interview 7/8 of a person because they only come in wholes. So I know that I need to interview 267 people. That's where they get to the 267. But even if I did this calculation, and let's say I got 266.11, I'd still have to talk to 267 because 266 wouldn't be quite enough. If I have anything left at all, I need to put another person on there. I can't just say, oh, I'll talk to 266. Then we're actually a little short. So we always go up to the next highest number for that thing. So I need 267 people in order to do that. Okay, that's the N. Assume that a recent survey suggests that about 88% of adults have heard of the brand. What if I knew that 88%? Well, then I know something about the p hat instead of not knowing. So then I would have the 1.96 squared times 0.88 times 0.12 divided by 0.062. So it's going to change the number if I know what it is. If I don't know what it is, I have to make some assumptions that change things a little bit. So let's put that in. 0.196 squared times 0.25. 0.5 times 0.5 is 0.25, and then over 0.06 squared. And that's probably not what I did times, dun, 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 dun. Yeah, I don't know what I did there. That's bad. Me being, I put 0.196 instead of 1.96. Hopefully you guys caught that when I did it. So don't try to be so fast. I knew that answer made no sense, that we had just 2 people, so that was not cool. Oh my heavens. I put 0.25 in there again. That's what I had there. I should probably delete that from the video, but it's good. What happened is I was being really fast twice, and I forgot. Jeez Louise. I forgot that I know what P hat is now, so I can't just put 0.5 times 0.5 in there. Duh. All right. And I have 0.06 squared. I think now I've actually entered the problem as I wrote on the page correctly. It took me 3 times to do it, actually 4, but so now what I have is 112.69. And again, I can't get a 6/9 of a person, so I would need 113 people to make that happen. So if you know something about the p hat, you don't need to talk to as many people, right? If you know something about that. But if you don't know anything, you just got to talk to more people, and then you're going to have to, so you have to make up for what you don't know by talking to more people. Given that the college, oh, it's down here, I'm reading ahead. Given that the required sample size is relatively small, could he simply survey the adults at the nearest college? Let's go back and say the brand manager for a brand of toothpaste wants to find out what his brand recognition is. How many adults must he survey in order to be da-da-da-da-da? Okay, it is a small sample. But if you just go to a college, you're going to get sample bias. Here's what I know about my college-age children. They know nothing about toothpaste. I could slip toothpaste in their drawer, and any time they would use whatever's in there, right? Is that the best people you want to go out and find that brand recognition? You definitely want to talk to people who do shopping for toothpaste on a regular basis, right? So that would be sample bias. You wouldn't get a true sample just by going and talking to everybody in there. It would not be a simple random sample, because then the only people that are possibly going to be brought in are the people that are at the college. It would be convenient, but that's it. So it's very possible it would not be represented in the population. A sample of the nearest is a cluster sample. Well, that's not really a cluster sample. It's a convenience. It's convenient to go and do it, but it does not represent the population. So we would say A. You can't just go talk to a group that makes it the best. I've had a situation where I've had students go out and get their own data, and the students wanted to find out how many times a month people went to a movie. And they went to the theater and asked people, how many times a week do you go, as they came out? Or how many times a month, or whatever it was. How many times a year. I can't remember. But the point is, they were asking people who were at the place. So obviously those people have some number to give. There's a lot of people in the population who never go. So if you want to do a simple random sample, you need to ask people in a way that it would cover more people, like how many people at the mall, people at the grocery store, people coming out of a theater, fine. But knowing that you're asking people from several different areas or walks of life, not just the people who you know for sure go. So that's how you can't just be super convenient. Okay, number 12, to construct a confidence interval using the given confidence level, do whichever of the following is appropriate. Find the critical z-score or find the critical t-score, or state that neither the normal nor the t-distribution applies. When we've been finding the z-score before, we know what the standard deviation for the population is. This is known. If the standard deviation is known, then you find z. If this is unknown, then you find the t. Okay? So this is the t-score. And then we have to figure out what it is. Now the t-score is the one thing that your calculator does not do. That's a bummer. You can't do it on there. However, we can do it. We have a 99% confidence. N is 200. And it appears to be, no. We want to find that critical t-score. So when you're finding a t value, we have to talk about the degrees of freedom. And I probably I don't know what I've talked about. I've talked about degrees of freedom recently, and I can't remember if it was somebody on here. So fast forward if you already know. The degrees of freedom are how many things you can do before you have to get down to business. In other words, if we were talking about somebody wanted to get a certain average on a test, like let's say you knew you had to average 85% on a test, and you knew that there were 4 tests, and you got these scores. You got a 77, you got a 92, you got a 90, and then boom, you had to do another test. And all of a sudden you had freedom kind of on these first 3 tests, but now if you have to get exactly an 85%, then you need to figure out what score you need to get that, right? And maybe it would be greater than, maybe you're okay with getting more than that, but you want to say, ooh, I don't want to go below that, so what score do I need to get? And then you'd have to go back and say, well, add up these 3 scores. What you'd want to do actually is, this problem is not that important to solve, but anyways, you want to you want an 85% times 4. Let's say they're all 100-point tests. You need 344 divided by 4. You need it to average 85. Yeah, so you want to do these 3 things, and that's supposed to average 85. All these things divided by 4, right? So you do 85 times 4. You need that to average 340. I just did a really, I don't know what the heck I was doing. 77 plus 92 plus 90 is 259. And then you have this last test, and then you'd say, okay, now I can figure out exactly what I need on that last test, right? So I would do 340 minus 259. That would tell me, oh, I need at least an 81 on this last test in order to get my 85%. And we could say greater than or equal to if you're okay with getting more. And so that represents an idea where you had 3 degrees of freedom, but then you have the day when you don't get freedom because you have to make that happen. And so the very easy degree of freedom formula is just n minus 1. There's always that last one that you need to make happen in the correct way. So if our n is 200, our degrees of freedom are 199. That's it. 199, one less than whatever that is. We need to know degrees of freedom. Okay. Now we have 99% confidence, which means we have 0.005 in each tell, right? That's the same thing we've been doing, but we need to know what this t value is, not a z value. So we can't use the z, the calculator does z-scores. You want to go find your t value on your table. Okay, so let's do that. I think they have the table printed here. Let me write down what these are so when I flip it, my mind doesn't go. I've got 0.005 in each tail. So I'm going to say in one tail, but I could have just left it and said, or I could just think of it as 0.01 in 2 tails, because on the T chart, we can look at either one of those. But this is what I have. And my degrees of freedom is 199. Now this is kind of stupid to me because if you have really big samples like that, the t values start to look like z values anyway. They start becoming very close to them. And so we usually don't talk about t values with an n of 200. We would use like an n of 12 or something. When we have really small samples, then the t values become important. But whatever, I'm going to do it. Because they are so close, that when we look at that, and I don't know if you can even, I think you can read it. Up here it says area in 1 tail, area in 2 tails. Look what happens when I go to area in 1 tail 0.005. Just below that, and in the same column then, is area in 2 tails of 0.01. So what I'm saying is they're going to be the same. You know, whether you look at 2 tails as being 0.01 or 1 tail as 0.005, those are the same. Okay, so these are available on, if you got a textbook from me, or if you got a textbook from the bookstore, you bought one or whatever, there's t-tables in your textbook. If you don't have that, then you can just print out from your homework, because they're in your homework in there, the table. But anyways, I'll be happy to send you an electronic version if you would like. Email me and I'll send you a version of the t-table. Okay, so what I know, I have degrees of freedom over here on the left, and I want to find my degrees of freedom, and then I want to find the tail, and then I want to find the value that way. However, we have 199 degrees of freedom. Look at our choices, 100 up to 200, because they don't even start delineating them because the differences are so small. And since the differences are so small, I'm just going to use the one that's closest, which is 200, even though our degrees of freedom was actually 199. And if I swing over here, it looks to me like 2.501. I can't really read that very easily. I'm going to tell you the truth. I don't think I have any better to print it off t-score stuff. I have tons of the z's. Okay, well anyway, it's right here. It could be 2.601 is what I think it is actually. When I look on the screen, it looks like 2.601. So that's going to be my critical T value. Let's take a look at it back over here. There's my choice right here, 2.601. So I had to find out what the area in one tail or two tails was, and I also had to find my degrees of freedom, and then I just looked that up on the chart. Okay, so not too tough. And 12 continued. That's nothing. That's it. 12. Oh, they had the z-scores posted too, in case you picked Z, but anyways, the answer was C. So let's move on. Number 13. Okay. Listed below are amounts of mercury in parts per million found in a tuna sushi sampled at different stores. The sample mean is 0.924 parts per million, and the sample standard deviation is 0.180 parts per million. Use technology to construct a 90% confidence interval estimate of the mean amount of mercury in the population. Okay, so how many different things were surveyed? 1, 2, 3, 4, 5, 6, 7. So our N equals 7. Do we know the population standard deviation? No. We know the sample standard deviation. Sample standard deviation is not the same. Sample standard deviation is S, right? And the S in this case is 0.180. What we need to know is the population standard deviation in order to use z-score, and we don't. And anyway, we have a really small sample, and that's a good indication of using T anyway. So we know our degrees of freedom is going to be 1 less than our number, so that our degrees of freedom is 6. We know we want to construct a 90% confidence interval. 90%, that's a really bad little drawing, but anyway, you get the idea. Maybe here's 90%, and so I have 10% on either side, or 0.05, 10% together, 0.05 on either side. So I could do area in one tail of 0.05, or in two tails, it's 0.10. Those are the same. You'll see them in this column, the same anyway. So that's going to give me my critical T score. Now remember, we want to find the margin of error, but now we're finding the margin of error with a T instead of the other thing. Okay, so let's go look at the formula for that. It's kind of vague to me. It's a little different than the Z formula, so I want to get that for you. And we can always go into our handy dandy Math Excel program. This is number 13. And we can look at an example and get the formulas as we need them, which is pretty cool. This is going to be a T thing. Here we go. It's the sample standard deviation. Well, it's T times sample standard deviation over the square root of N. So let me write that in a way that's actually legible. That's going to be our E. Okay. Oh, you didn't see me write it. It's so sloppy. Okay. Anyway, let's go back. I don't know why I did that. All right. So let's go back now. This was my first attempt at writing that down. Remember how you find a confidence interval is to take the sample mean. Oh, this isn't a proportion anymore, right? It's a mean. And you add and subtract the margin of error, and that gives you your two values. When we did it before, it was proportion. Now we're talking about a mean, and so we're going to get some value that's between mu, that mu is between, these two values, so that's what we're after. We need to first go out and find out what our critical T value is. So let's look at the area in two tails is 0.1, and our degrees of freedom is 6. Yeah, why did they give us... Oh, that's passed. Where's our t-best table? Here it is. Okay, we have a degrees of freedom of 6, so we're down here. And our area in one tail was 0.1, or in two tails 0.05. They're the same column, so we're good. And then I'm just going to go straight across, and I get 1.943. Okay, so 1.943 is our margin of error. Again, you can see that it's actually negative 1.943, positive 1.943. We're just talking about the positive of that when we were doing this. And as I was saying before, I should have done it before, when you have these small samples, you're talking about t. And so it could be a little different than what you would get for a z-score. But not terribly different, because there is a general shape. This looks more like a z table, a z distribution. T distributions are a little pointier, a little less wide. They have a little wider. They have a more, a wider standard deviation, because we have these kind of random samples, not that many to go on. So I'm going to find my margin of error, and I'm going to take that and I'm going to do x bar, which is 0.924, and subtract 1.94. Oh, I didn't find it. I just found the E. I just found the T value, sorry. Still have to go do this. Sample standard deviation divided by the N, which we said was 7. Sorry, did not finish that. Kind of lost my train of thought, apparently. 1.9 and 1.943 times this fraction 0.180 divided by 7 gives me a margin of error of 0.050, rounded to 3 places. 0.499, which is 0.050. 0.50, and then I'm going to do 0.924 plus 0.050. That doesn't look like what they have, does it? Well, let's see what we get and see what's happening here. 0.924 plus 0.050. Yeah, I'm off somewhere. And sample standard deviation, I got that right. 1, 2, 3, 4, 5, 6, 7 is the N. 90% confidence, 0.05 in each tail. Maybe you guys see what my mistake was. I don't yet. Oh, was it the square root of N? Oh, jeez Louise. Yeah, that's what it was. I wrote the formula down right, but I didn't put it into my calculator right, because look what I did. I just put 7. You know, I have to say it because I say it frequently. It's okay to make mistakes. It's not okay just to stomp away math when you make a mistake and say you're no good at math and you're going to quit forever. Because, you know, people make mistakes, and that's what we're going to do. So that looks like a little better answer, 0.132. This is just going to have to be done again. 0.924 minus 0.132. and 0.924 plus 0.132. When I first started teaching this course, I went through and worked every problem on the computer and entered my answers. And I got it wrong so many times. Half the time, at least, it was because I didn't round to the number of decimal places they said. I would round to 2 and they asked for 3, or I'd round to 3 and they asked for 2, and they just, boom, they don't count it right. So you have to read the directions about rounding. Read the directions about rounding when you're taking the test. I will give you partial credit, but I'm not going to give you full credit if you haven't read the directions. I make that mistake, true, but I don't want you to make that mistake. So I had to really get good at reading the directions, for one. But the other thing is, sometimes I would do something doofus like this, like forget to do the square root and make a mistake, and then I'd be like, wait, that's not what they're getting, you know, like whatever. And then I have to go back and troubleshoot. when you make the mistakes are when you learn the best. Making the mistakes really is a great teacher. So instead of thinking of it as a downfall, think of it as, wow, I had a chance to really learn something here, and it was useful. So I didn't write that down right, but those are the two answers that they got now, 7.792 and 1.056. Okay, so you have to go out and find your margin of error. In order to do that, you need to find your critical t-value. And then you take your mean for the sample and you add and subtract that margin of error, and that gives you your two numbers in this format. Okay, almost done. Chin up. Let's see what we can do. All right, a data set includes 103 body temperatures of healthy adult humans, for which X bar is 98.3, and the S is 0.73. That's the standard deviation for the sample. We don't have a population standard deviation. In my head now, I know, whoops, we're talking about T, right? What is the best point estimate of the mean body temperature for healthy humans? Well, the best point estimate for the mean is X bar. So it's X bar, that's 98.3. Did they write it as 98.3 or did they write it as, man, this one goes on forever. Jeez. Yeah, they write 98.3, so that's what they want. Okay. Using the sample statistics, construct a 99% confidence interval estimate of the mean body temperature for all healthy humans. Do the confidence interval limits contain 98.6, and what does that suggest if it does or it doesn't? We all think 98.6 is the standard. So if we have actually go out and take a sample and find out that our confidence interval doesn't include 98.6, we could say like, whoa, that's not right. And most people in my family don't have the 98.6 anyways. Mine's way lower than that. My son's way above that, so whatever. Maybe 98.6 is representative. We're going to see. So I know my degrees of freedom because there was 103 people in this survey. My degrees of freedom is going to be 102. But as I showed before, when you have 102, you're just going to use 100 because there's nothing that's going to correspond to that exactly. We're talking about 99% confidence interval, which means the area in two tails is 0.01. And we could break that down to 0.005 if we wanted. So I need to go find my critical t value. I'm going to use 100 as my degrees of freedom. And I had a 0.01 in one tail, which is corresponding to 0.005 in two tails. And if I come down here to 100, I get 2.626 as my value for T. 2.626. And then I'm going to find my margin of error by taking 2.626 times the standard deviation I was given, 0.73, divided by the square root of the population, which is the square root of 103. Let's see if I can actually enter that into my calculator correctly the first time. So I have 2.626 times this fraction, 0.73, over second function square root of 103. If I hit delete, I can just delete the last few things instead of hitting clear, which you have to start all over, which is a handy thing to know when you don't have to enter the whole thing over. Anyway, let's do that again. It's 103. And what I get for E is 0.189, rounded to 3 decimals. That seems to be where they're wanting me to round. But I need to add and subtract that to my X bar. So what is the confidence interval estimate of the population of the mean? Well, I'm going to take 98.3 and subtract 0.189 and 98.3 plus 0.189, and that's going to hopefully give me my two values, 98.3 minus 0.189 is 98.111, and 98.3 plus 0.189 is 98.489. And so there's my two numbers, the lower and the upper bound of my interval. And we can check to see if we did the calculations right. It's 3 pages back here. 98.111, 98.489. Does the confidence interval limit contain 98.6? 98.6 is not contained, so no. What does this suggest? It suggests that the mean body temperature could be lower than 98.6. It suggests the mean body temperature could possibly be 98.6. It suggests the body could be higher. Well, I don't think you're going to need a lot of help answering that, but obviously our range is lower than this. So it suggests that we could maybe be lower than that, right? So that's what you want to answer. And that's A, could be lower than. All right, so maybe we got that wrong. Just looking at, before I do 15 here, they have the critical T values printed, and they also have over here the picture. And you can see this picture, it's a bell shape, but remember the normal distribution has more, it's a little gentler, not quite as peaky of a bell. So the T values are similar, but they are a little different because of that, because of the peak. So, but as you get more higher and higher, like a 200 sample, it starts resembling more and more like the standard distribution for Z-scores. Anyways, okay, let's see what 15 has in store for us, and then we could be done with this video. In a test of the effectiveness of garlic for lowering cholesterol, 44 subjects were treated with garlic in a processed tablet form. Cholesterol levels were measured before and after the treatment. The changes in their levels of cholesterol have a mean of 3.9 and a standard deviation of 17.6. That's what their study found, which means that's a sample, not a population. What is the best point estimate? The best point estimate is going to be the mean that you found in your study. Construct a 90% confidence interval estimate of the mean net changes. Well, also I know that we had 44 subjects. In order to find this, you need to get your area and the T value, your critical T value, and that's going to require that you know your degrees of freedom, which is 1 minus n, so that's 43. And it's also asking you to know what the area in one tail is, and since we're talking about 90%, we're talking about 0.01. Right? Also, if you want to do area in two tails, you would look up 0.05. Those, again, I've showed you several times, it would be the same. Once you have your critical T value, you can find E by doing this little calculation that we've done. And you can find your interval by taking your X bar minus E and your X bar plus E. And you can write your interval in this format, right? And then it says, what does the confidence interval suggest about the effectiveness of the treatment? If your interval contains 0, that means that possibly there could be 0 effect, right? And that means that the treatment's not very effective. If it doesn't contain 0, if it goes up a little, then you say, well, it seemed like it was a little bit effective, right? So that's what you want to check and see, and then answer that question according to what you found for your levels. The process for finding your confidence interval, whether you're using Z or T, is the same. You find your margin of error, and then you add or subtract that to your mean or your p-hat, whichever one, your proportion or your mean, whatever you're talking about. The difference is to find that T value and the Z value. And when you know that you're using the T value is when you're not given a population standard deviation. And there's no way we could have a population standard deviation. Like, how would everybody know, everybody in the world's reaction to garlic? I mean, we haven't tested that many people on that, right? So it's really more realistic to think that we don't ever know what the population standard deviation is. Why would we? Like, that's like something exclusive to your little study right now. Who's done that for the whole population? There are some things that have been done enough that there are population standard deviations, such as heart rate for women or something like that. But average heights and those kind of thing, average age for childbearing women. I mean, there's studies that have been done enough that we can say we pretty much know that, but most of the time in these little studies like this garlic thing, we're not going to know it, so we're going to have to use the sample standard deviation. I'm not going to work this problem out. You've had a chance to look at it while I ramble on, and if you'd like to see the answers, then I will take you back to those if I can find them. Pages and pages of wasted print. 3.9, that's because that was the point estimate that we were given. And then our lower level was negative 0.56 and our upper level was 8.36. This suggests that our range not only includes 0, but it could be negative. In fact, it could have a negative effect. So it doesn't look like it's very effective. That's probably what D says. Okay, that's it for today. Have a great time doing your stats, and we'll see you next time.